So I think I just start. So my name is Hiren, and I'm a postdoc in the group of Tobias. And so today it's the last day of this workshop, and we're going to talk about the axial symmetric systems. So the topic of the day, so this very general slide will be will include three parts. The whispering gallery modes, that will be mostly me. And then the second slot will be by Miles, talking about dispersion engineering, optical cavities. And then we will have an invited speaker talking about the thermal noise. Yeah, so let's just get started. And the first part, axial symmetric system, number one, whispering gallery modes. So this is the picture I generated. So if you can find the model in the folder, there's a full model under the folder of COMSOL, and the subfolder of axial symmetric system 1. So you will find the full model, and then you open it, sort of the way you will see something similar. So before we really go to the real question, or how to do the modeling, so some basic concepts. First of all, we need to know, like in this kind of simulation, we're searching for electromagnetic waves, and which is usually in this way pretty general. But we know that, for example, the electric field would be consist of 3 components. I mean, in space. And then most of you may probably know the method or the idea of separating the variables. Then eventually each component of the field can be further separated into a complex amplitude together with the spatial and temporal carriers. So in this simulation, we're going to looking for eigenmodes. There are actually 2 ways of eigenmodes. One is just in a waveguide, or in a sort of median fiber waveguide anyway. And then in this way, what you need to know is you want to looking for a sort of solution with respect to a frequency you preset. So in this way, you can define the frequency, and then you're looking for amplitude and the so-called propagation constant. Then eventually you can fully define the field, so which means you find the solution. And there's also another way to looking for eigenmodes, which is in a resonator system. So in this way, we know that the resonator would actually give you the boundary condition, which means your propagation constant times the cavity length should be the integral order of 2 pi, which means it will find the phase match over each round trip in a cavity. So in this way, you are actually try to define or preset the so-called the wave number, define the mode index. Let's call it like in this way. And then you will try to looking for also the amplitude, but this time the frequency. So it's actually a little bit different. So in this way, you are setting the frequency, looking for the propagation constant. And this way, it's a bit like inverse. So if this is clear, then we can go to our topic. So we are looking for whispering gallery mode. It can be such a cavity. I mean, whispering gallery mode, definitely, in a ring cavity. And such a ring cavity can be as large as the sample cathedral, the dome of that. So this is first explained in the place, and then the whispers can be traveled around the dome of it. And also, such a mode can also be in optical micro-ring resonators, which is very small structures. And in our group, we are investigating a bunch of researchers and talking about on these topics. So if you ask me why microresonators, I would love to show this very famous slide within the group. So basically, we try to combine a very high Q resonator together with the nonlinearity. So eventually, we can try to pump the resonator with only 1 wave or 1 frequency wave, CW wave, and then use the 4-way mixing to excite the light conversion into another mode. And then eventually this is called a frequency comb generated in the microresonator geometry. And compared with really the normal mode lock lasers, we know that microresonators should have compact size and a very low threshold power because the power is scaled inversely with respect to the Q factor and also inversed by the effective mode volume, and which is very small in the cavity. And then in this way, the free spectral range will be as large as 10 to 1 terahertz. And then in this way, we can really get into the microwave domain. And also the bandwidth can be as large as 1 octave, especially in the telecom band. And in this way, we can also generate sort of the soliton, which means you have a pulse which can be self-persistent and traveling inside the cavity, round by round. And its spectrum looks like this. So this is consists of like hundreds of modes inside, and they have a very well-defined profile corresponding to the soliton profile in the time domain. Okay, so this is just a very basic concept, and based on this microresonator frequency comps, so mostly half of the group is involved in this research. And then we do both laser physics and soliton dynamics investigations on the very fundamental level. But on the other side, we also do applications, including telecommunications, spectroscopy, as well as low noise microwave generation. So if you find new faces today, so most of them are coming from frequency comp research. So let's back to the implementation of looking for modes. Apparently, if you want to do investigations on microresonators, the first step is to know what's the resonance. I mean, what's the frequency of the resonances and how the mode looks like. So in COMSOL, we can implement and then to find such an eigenmode. Usually, COMSOL support like 3D geometry, so which means whatever structures you can try to figure it out how to solve. But there's also a way, I mean, if you're looking into a ring structure, you know, like it's definitely 2D axisymmetric. So you may ask whether COMSOL can deal with that. So the answer is absolutely yes. But before 2014, actually, mostly you must configure by yourself the weak form PDE module. So which is mentioned, as I remember, earlier Monday by Amir. So this is pretty complicated. If you want to use that model, you need to know several keywords. First of all, what's the weak expressions? So anyone knows? Yeah. And then penalty term. And also, because you are using the very basic PDE module, which is like 2D component, not as this one, the axis symmetric. So eventually, you also need to figure out how to convert the coordinate from the Cartesian to cylindric. So overall, it's very complicated. I mean, as I joined the group, I found this really a difficult way to go through. But actually, if you are really interested, there are 2 papers. So the guy, Oxborough, he actually developed everything for us. So there's one paper talking about the very fundamental physics behind how to do everything. And there's also another paper titled like Configuration of COMSOL Multiphysics. So which means he tells you step by step how to really configure your software. So which is pretty good. So 3 years ago, the last workshop we organized, actually most emphasis were put on on this way, so how to configure, because at that moment, COMSOL, the normal or the very friendly model, wave optics or radio frequency cannot handle such a problem. But now, things are changed. So in this presentation, I'm going to just focus on the wave optics and using the 2D axisymmetric model, because it's finally implemented. So this is sort of the, so if you have COMSOL already installed, you need to open it and then go to the wave optics. And today, the very basic geometry is on the toroid structure. So in this way, we're only going to simulate the small area over there, which is good enough to help you to define the eigenmode that will circulating inside the toroid. So this is very basic geometry. You have in the folder a model, and I'm not sure if anyone has already found that. Okay, it's under the folder of software COMSOL and axisymmetric system 1. So there will be the axisymmetry system, and as I remember correctly, there will be the simple model or the full model. I mean, depends. So I'm going to show step-by-step things regarding using the simple model because it's mostly empty. So I will configure by hand. And the full model is already prepared for you to look over and review everything we're going to talk about. Yeah, so this is the geometry. And I also created a table under the COMSOL, like in this global parameters. So by this step, if you open the simple model, everything should be there. So let's just try. Okay, so this is sort of my simple model. I hope everyone can see that. So here, if you expand all the configurations, you can see the parameters as shown in the slides. It's already there. And this is sort of the very simple geometry. And under the geometry, you will find like some of the very key parameters are defined with the link to the table of parameters. Okay. So under the component, you find it's pretty clean, which means nothing is already configured. So in this way, you right-click, and then you try to add physics. Okay, then in this way, as I mentioned, we're going to use wave optics. Okay, it's here. If not, then you will try to try physics here. So you would find it. Under wave optics, we're going to do the frequency domain. So frequency domain, add to component. So now in this way, you find some of the part is already added, and then you find a little cross around the material, which means finally you define a physics, then the system will automatically looking for materials, parameters suit for the problem. Then here in this way, you can already define two positions. One is really the mode index, which is under the physics, electromagnetic waves frequency domain over here. So looking back to the parameter table, we actually have that defined, which is called index M. So you just copy index M to that place. So it will automatically link to the parameter. So in this way, you don't need to really define, random numbers inside. Then you forgot to change. Everything is left over. So we say that we try to control using the global parameters in this way. And under the wave equation, I mean, you can try to look into the equation, which is very basic for looking for mode, but it's already compiled in the cylindric coordinate. Okay. And then here, you can pick up different parameters linking to the material. So here, automatically in default, it's a refractive index. So that's why for materials, so far, nothing is defined. So if you try to add materials from library, for example, we need to know this is sort of the air, usually. So we find air. Yeah, so we find, for example, building, air. And then we add to component. So now you have air. And under the material, you will find actually, so this is the new version, 5.3. Previous version was not that good, actually. So Under here, you will find, because you already choose refractive index under your physics, so the material side, it will configure what are the key parameters. If the key parameters are already set, so you will have this, this kind of mark checked. If it's not, let's say, let me see if I can change, yes. So if it's not, then you will have a sort of sign called stop, if you look carefully. So in this way means the little cross comes again. You are not allowed to compile because the key parameters are missing. Okay, so put it back. So this is the air. As we know that air should not including the material side because it's like the surrounding. So in this way, we need to add another material. So I would try something different. Let's say blank material. I give a name like silica, probably. I mean, it's fine. But as I said, the very key parameter will be the refractive index. So you need to check whether there are refractive index set or not. Because it's blank, apparently at the moment it's not set. So under the basic, you need to find output, and then you go down. There will be somehow I cannot find. Yes, but I want to find the refractive index. Well, yeah, this is the permittivity, so it's not a refractive index. So in some way we need to define. Okay, anyway. Yeah, previously it should be there. I mean, you will find the like electromagnetic wave and then refractive index. Yeah, yeah. Okay, anyway, we just find looking for the library because silica are everywhere. Oh yeah, you're right, probably. Yes. So under the material, if you click to choose the area, actually, you will find it will automatically generate the parameter linked to the refractive index. So here, if we look back to the material table, there's also an index defined. Give a name of N core. So here we just put N core here. I mean, as I said, the material is just a name. I mean, and what really matters is actually the refractive index, the parameter. Okay. Okay, this we don't need. So now you find the cross is gone. So far we have defined the material, so air, yes, and silica, yes, okay. And then for the physics, we have already also defined, yes. And what's missing here is actually the sort of study. So we need to define a solver. So we go back and then add study. So under here, we try to looking for eigenfrequencies because, as explained, this is the cavity system. You define the mode index. You're looking for the amplitude together with the eigenfrequency. So we need to looking for eigenfrequency. So under this, you can also try to ask him to show you the very default solver. So there are more configurations inside. Okay. So eigenfrequency. So here, you can design the number of eigenfrequency, let's say 5, or in default 6 is okay. And if we go back to the table, actually I write a very long equation, a sort of long equation here to give you a sort of initial guess. So this guess is based on the boundary condition and using the refractive index of the core material, and eventually you can sort of find a start point. So this initial guess should be input under here, like search for eigenfrequencies around . Okay, and here you can define several ways. So here we choose larger in the real part. Okay, so everyone can follow. To be sure that we can find all the modes, we can also increase a little bit more the number of modes searching, and then we go to 10, or you can try even more. And then another problem is really on the accuracy of your simulation. So, sorry. It's under the very top side. So you go here, and then you right-click. You can add study.
No, after you did it, we don't have the solver configuration.
Yeah, that's study, and then you can show default solver. Yeah, it's in default because each time you try to start the computing, and then it will automatically configure. But if you want to preset some of the parameters, you can ask him to show now. So over here, I just want to mention one feature is the relative tolerance, because in default it's showing to be like 10 to the minus 6, the order of precision, and actually we are looking for eigenfrequencies. So if you're looking for eigenfrequencies here, it's actually a pretty large number. So it goes to 190 terahertz. 10 to the 12 or 10 to the 14 actually. So if you want to maintain a certain accuracy, actually you need to really push down the tolerance. So let's say to be 10 to the minus 12. Okay, so in this way you are already in the level of 100 hertz precision. Yeah. Then what's missing is actually here the mesh. So mesh is not properly set. I mean, you can see it's pretty bad. And definitely it will be not that precise eventually. Even the tolerance of the simulation can be very nice. But actually the mesh is very low, which means the geometry is indeed not well defined. So the version 5 of COMSOL actually include a physics-controlled mesh. So if you enable that, you can actually keep going on to define, for example, what's your wavelength, and you just define the minimal vacuum wavelength. If you say it's 1 micron, and then you go back to the mesh, you build all, you see, it will be pretty dense. Okay, maybe this is too much. You will say, like, especially for this workshop, because it will take time to solve. And then we can go forth and back to change. So you can also find the user-defined and the maximal element size in the free space. So in this way, I would suggest 0.4 micron. So you can taste a bit in different options here, like what would be the frequency, what would be the wavelengths, would be from the user-defined side. But I just tried several times in the past days, and I realized that in this way may be better. Yeah, it looks okay. There's also other ways to really do very precise mesh, which is called like you locally put very dense mesh inside. So here, you're no longer, yes?
How do you, so I set this parameter, you just change that, but for some reason the mesh doesn't actualize. If you click something,
What parameter you are changed?
oh, I changed the, again, this physics control.
Yeah, so you enable the physics control mesh. Yeah, okay. Under the mesh, you need to build all. There's a little button on top. Yes.
Where is that button of physics control mesh? Not in the mesh.
It's under the physics. So here, and then you find. Yeah, there's also a way to do very nice mesh. So under the mesh, you can going on. You can add actually a free triangle mesh. So here you can really pick up, for example, domain. So if I want to put really nice mesh over this little area, so you put the free triangle mesh over here. And then under that, you need to configure the size of it. So you can define to be finer or extra fine. Then here you have two options. You build select it. If it's not too good, then you choose extremely fine. So you find it's actually better. Okay, because you pick up the free triangle and there's only one area is chosen. So actually the system will know that all the remaining areas are not configured. So you need to also add another free triangle mesh and then let it to be on the remaining area. Okay, so in this way you build all. Then you will see partially the core area is actually dense meshed, but the remaining part looks okay. Yeah. So this is just a very initial step to let you know, like you have different options. You can let the system to define because it's physically controlled. You can also manually configure different level of mesh at different areas. So I think in this way we can try to compute. Sorry? The boundary conditions? We let it to be default in this way. Yeah?
What's that very right rectangle at the edge of the...
Ah, okay, yeah. This is defined because in the later part, I'm going to talk about the whispering gallery loss. So it's already defined there. If you find it's really annoying, you can disable it. So let's see. Yeah, it's gone. Okay, but you can also check all the things remaining. Materials, yes. Right? And the refraction index are configured correct. Okay. So let's try the compute. Do you know where to find the compute button? Usually it's not everywhere, right? So either under the study, here you have the compute, or each time you click the study, then on the top you have the compute. So go ahead. Some little tips here is that during the simulation, you can also look into the log file, and it will find your error estimation and how it's going down. Amir also showed you like to read this kind of plot, like you can find your accuracy level. So we define to be 10 to the minus 12. So if it's reached the 10 to the minus 12, it will come out and to be solved. Okay. Yeah. Because you are looking for eigenfrequency, and the eigenfrequency at this moment is pretty large number. It's 10 to the 14 usually.
But when
Yeah. But it's actually the called the relative. It's called the relative tolerance. So, which means it's maybe usually doing just 1 minus step. Sorry. Of your solution.
But what is your solution? Is it the field or is the eigenfrequency?
It's the eigenfrequency.
Okay.
Yeah. Because this is like the eigenfrequency solver. So you're looking for the eigenfrequency, and then that part is the eigenvector. So it's pretty, I mean, it's pair to pair.
Yeah, okay. Yeah. No, that was just to clarify
Yeah.
to what it corresponds to the eigenvector or to the eigenfrequency, the tolerance.
Mm-hmm. Mm-hmm.
You know, your electric field, you can do the -12 precision.
Mm-hmm. Yeah, it's always eigenfrequency. I mean, we tried a couple of times afterwards, like for different level, and then eventually, with a nice precision, you will see the confinement is actually being more precise. Otherwise, you will stop at certain level. So yeah, so here we have already find something, but apparently it's not the mode. This is just because the radius of the band may be too much. So you see most of the beam are actually out leaked. So it's not within well confined within the geometry. So let's see if all over here you can have some of the wave. So in this way, you find it's already pretty annoying that each time you have to pick up different frequencies, and then to looking for different field. So COMSOL can actually give you a better way to look into all these things. Okay. So we can try it again if you want to quickly looking for some of the mode because here the radius is pretty low. So I try to increase a bit the radius, for example, to be 50. Okay. And this one will be like 300. Yep. Then you find okay. So let's do it again. So again, you can look into the log file for the confinement. And then also here, you can find at which level, how many modes are solved out. Oh, yeah, it comes. So, sorry? Huh? The mu, okay. The radius 50, index 300. I mean, there are physical reasons why we choose these things and why the simulation becomes, more comfortable eventually. You can already define mode. This is because more the bending you set, and eventually the potential of those leakage modes are higher. So that's why the system will find those fake modes instead of the real modes. So if you just put the radius a bit longer, then the things can be solved. Okay. Yeah.
So here you set the boundary conditions as perfect electric conductor.
Yeah.
You explained that this is like a mirror for the electric field.
Yeah, but this is because the mode component is still in the center of the box. Yeah, it doesn't matter at this moment. Okay. Yes. Yeah, but we are going to mention the PML soon. Yeah. Okay, so this is the very first try. And if you open the full model actually there, I prepared more details, but let's go back to the slides. Then I will show you. Oh yeah, cool. Okay, thank you. Yeah, so we will stop by this table of parameters. And now if we're going on, so step by step, you can try to configure the materials. So again, don't forget to look for those check if the key parameters are configured or not. For the other parameters are used for other questions, but not here. And then physics, You need to configure 2 steps here is that you need to configure the mode index as MOSO mode number, and then link to the and link this displacement to the reflective index. So here, if you change, then go back to the material side. Some other marks will show up. So in this way, it's pretty smart to help you to configure or to check. And for the mesh, just some key points. You need to find a trade-off in between the precision level you required and the time consumption. Apparently, a very heavy mesh will take longer time. And just briefly mention the locally dense meshing, so you can try. And there's also a very important side like benchmark. So if there's an analytical solution, you need to compare before you really make your simulation in reality. And if there's no analytical solution to support you, then you need to gradually change the level of mesh to be more and more dense. Eventually, you can find the overall solution is convergent. Then you find you say that okay, I'm okay on the mesh level. So the idea of benchmarking. And then for the study, yes. So this is the equation to remind you, like based on the boundary condition. So you need to know, like, if you set the M already inside, and mostly the geometry that the radius is already defined. So actually, the only thing is you can have the pre-guess of the material index, and with this one you can search for eigenfrequencies. So you know the direction actually. If you set the core material to be your initial index guess, then eventually the effective reflective index of the mode will be lower than that. So the n is smaller than n core. Then the eigenfrequency should be ideally larger than this value. So this is exactly the one we set in the parameter table to help you identify where to start. Okay. And again, the tolerance. Yeah, computing. So this is sort of the way you would have the result. So apparently you can see the mode distribution, which looks very beautiful. And you can also looking for different components. And also you can reconstruct the field if you open the full model. And then there will be a 3D, very nice field plot over there. And you can also do animations. So this point we have already know. But other than this, what else? Okay. So apparently, COMSOL can do much more than that, or more than these things. So here, one very nice tool I want to introduce is the calculators. So in COMSOL, you can also define calculators. For example, you do the integration. Yeah, sorry. And then by having that calculator, you can also define probes. So which means you can calculate automatically, for example, the effective mode volume, which looks pretty complicated, but you can compile in a one-line calculation. So in this way, okay. And for the integration, you can also define area, like which part I want to do the integrate. So eventually, with all these things, you end up with a very nice or full information table, which tells you everything. For example, here I defined the confined ratio of 2 components of the electric field, like in the radius direction or in the axial direction. So it's defined like ER ratio, EZ ratio. So among all these tables, you will find actually this frequency locates a mode, right? Because you have the EZ component giving you almost close to 1, which means it's like 96% of the wave is inside the overall core area. And again, another one, pretty high level, which means this can be the fundamental, and this is sort of the high order mode. And also, you can define the effective mode volume, so it's 10 to the minus 15, minus 16, whatever. It depends on your geometry. Okay. How many time I have? Yeah, I'm sort of already behind the time, but I will try to be fast. So it's still not over yet. Okay, so things like, okay, I have that table, everything seems okay. But here, you forgot one thing. What's that is actually the material dispersion. Because we know the refractive index of the material is usually frequency dependent. So in this way, you see like you define sort of the index and then you locate and then you find the eigenfrequency. But in return, the frequency will come up and then refresh the index again. So this problem eventually leads you to do different iterations. I mean, you need several iterations to find if you can already locate to be very precise, okay? Because you set the index and then it gives you the frequency, but the new frequency will give you new index, so you do it again and again and again. So iterations, pretty clear. And since you are going to the problem of iterations, one very clear question is whether your iterations will be convergent or divergent, right? So here we just quickly show that in which case you would have the convergence. So we know right now you're actually trying to find the cross point because one side is the frequency-dependent refractive index, n omega. The other side, this kind of blue curve, is defined by the boundary condition of your cavity, right? This is the boundary condition, and then you will find the index as a function of frequency. So it looks over there. So hopefully there will be a cross point. And then you're just going to locate carefully where this cross point is. So if you recall again what the simulation you have done, so we say that you pick up a frequency, and then you are in the material side, so it will give you the very initial index. So you tell the system, yes, I have the frequency, I have the index, so give me the solution, right? So apparently system will just, the COMSOL will give you sort of this kind of point. So you are here. This is because the solver is looking for the eigenmode in the cavity resonator system. So apparently it will looking for modes around this curve because M is also set. So you are here. And then you say, oh, the frequency is actually changed. So you have to go again to follow to the refractive index side. So eventually you end up with sort of iterations. And in this way, it seems perfect that you can finally get into the central cross point, right? But then if you try to confine such a problem mathematically, you find, yes. So the necessary condition for the overall convergence is that you must have the slope of the refractive index change pretty small or smaller compared with the boundary condition. Okay, so this is the convergence of such a problem. Yeah, so to do that, I'm sorry I do not have a lot of time, but we can discuss afterwards. So here is just using the COMSOL MATLAB link provided. I'm not sure if you have already heard COMSOL MATLAB or at least in this workshop before. But here, just a very basic transfer in between MATLAB and COMSOL is you need to know that what you have done in the software, how it shows up in the MATLAB script, right? So one side is transfer a model to a script. So to do this, it's pretty easy. So you save as your model into the script. That's it. Okay. And the other side is that now you have the script in the MATLAB, and then you somehow by mistake, maybe you type something wrong, and then you want to see the consequence in the software. So how to transfer the model back. Then in this way, there's one command among tons of commands that you can use. So if you want to know more details, you need to look into the menu of LiveLink, COMSOL MATLAB. And then here the command is called like mph save. So you save your model, which is a structure in the MATLAB, and then you define the name, which is a string. So eventually you can end up with a file, and you can open this file under the software. Yes.
What is exactly the model? So what is exported exactly? So
it's the very general model. So on the file, right, left, top, you save as everything.
So I mean, in MATLAB, so what can I access in MATLAB? I mean, if I've been running
You need to run. Yeah, we have a simple example there. And also in the folder, you also have under the subfolder exosymmetric, you would have the MATLAB link. You have that folder? Okay. You need to open, because there you only find MATLAB scripts. You need to open the runme.m file using the COMSOL MATLAB, not just opening MATLAB. If you install COMSOL properly, so let's go to my, if you install COMSOL properly, then you would have COMSOL multiphysics and also COMSOL multiphysics with MATLAB. So you need to open this one, okay? This will give you a chance to compile your password or anything, and then, by the way, open the MATLAB. So.
But can I use just so if had I exported the mode into a .m file, then I can load this.
You can look into that script, yes, but if you want to run it only in MATLAB, no, because a lot of lib file is not included.
Manipulate the outcome of a simulation later.
No, no. Yeah, you want to make it valid. You must open COMSOL MATLAB, so not only the MATLAB software. Okay. Okay, the time is quite limited, so I will not really show this example, but all the files are already there, and you can practice yourself in the exercise session. So the last topic of this one is called the whispering gallery loss. So intuitively, you will find maybe this sort of cavity is not that perfect, it's not complete, because you have the mode actually circulating, and it's defined by the boundary here. I mean, it's confined. So with respect to the radius, when the radius is increased more and more, you'll find this bunch of mode will have the same propagation or the phase velocity. So which means the outer side will be more faster than the inner side. I mean, this is linearly scaled with the radius. Then eventually the phase velocity really adds the long outer way will be higher than the speed of light, which is not possible. So this means at that moment those components will be just will just perform as leakage. It will not follow any way to the mode. So this is defined as the whispering gallery loss, and apparently there are very complete physics behind, which is also defined as tunneling loss from a barrier energy, so which means you would have the barrier created, and then there you have the eigenmode of the beam, and then over there, after the potential going down to 1, and then you find its unbound propagation. So which means this part of the energy is got lost. So yeah, you can look into thesis of Tobias or ask him directly. He's there. And in this way, we can define what's the so-called radiation Q, because the system is not, infinite perfect. Then you have the sort of intrinsic loss inside. And also, you can also define the tunneling distance, which is defined as the depth of the evanescent wave. Okay. So now we come to the boundary condition of COMSOL. So ideally, I remember there's one question. So normally we just in-depth set like PEC or PMC condition in the COMSOL. So in this way, I think that's sort of picture I copied from Amir 3 years ago, and he has very nice conclusion saying, normally we're just simulating something within a metal box, which means you have pretty close the boundary, and this is in the logs plot, and you will see like the interference of the wave when it hits the boundary and get reflected. Okay, so in COMSOL, using the perfectly matched layer, so what you are doing is actually you open the box. So in this way, you can already find that the interference pattern is gone, and then you have sort of the absorption somewhere, and this perfectly can match your physical problem to looking for the radiation Q. Okay. Yeah, also, so benchmarking is also very important with respect to this topic. So you can find an analytical solution according to microsphere, silica ore, or microresonators. And in the other way, there's also a very nice paper published looking into how to really do the benchmark between the COMSOL and the analytical solution. So I also prepared one model for you looking into, and in this way we are using this little area around our model defined previously. And you have to be careful. In this way, we try to use the physics control, the mesh, and the mesh of this area because you define it as to be the perfectly matched layer. So eventually, it's not free triangle meshing. And this is reminded by Miles to me yesterday. So it's actually a rectangular mesh. So in this way, you are avoiding, yes? Okay. You can ask.
So this very square mesh is necessary for PML?
Yes, yes. Yes, indeed. It depends on which kind of coordinate stretching type you are using. Which type you are using for the system. Here you use cylindrical, which means overall in the 3D plot, you also have the radius like expansion of the mesh, but in the cross section it's rectangular. But if you use for example other ways, you can have a trick, then it will automatically define differently. So which reminds you that if you try to do the manually do the meshing, you also need to follow the same way. And physically, it's just because using triangle, it will give you reflections to different areas, different directions, which will be not that precise. Okay. So this model is also saved under the solver, and if you're not clear where it is, then let me know. So then in this way, we can define the Q factor, which is the real part divided by twice of the imaginary part of the eigenfrequency. So one example, you try to configure the model using the same table, and then you're looking for the eigenfrequency around this value, and then you'll find a Q, radiation Q. So finally, to conclude my part, so I hope like after this way, including looking to different files, and after the exercise session, you have some way to learn. Then you learn how to solve the WGM in 2D axisymmetric cavities. And you briefly know the COMSOL MATLAB link to precisely locate the mode. But I hope you all understand the conference and the iteration, why we need that. And the last part is regarding the respring gallery loss. If you're still not that clear, so read papers. I think that's all from my side. Thank you.